Alright, so in this video we're going to continue our discussion on trying to find the area of a region between two curves. And here we have this example. I'd like you to find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So we have a lot of graphs that we need to plot on our plane here. But they're not too bad. I mean, x squared plus 2, that's a parabola. So I'll go ahead and sketch this one first. So I'm going to sketch this one in green. So x squared plus 2. That would look something like this. So let's see, there's 2, and I would have some type of parabola that maybe opens up like that. So I'm going to label this y equals x squared plus 2. The next function that I have is y equals x. I'll label this one in turquoise here, or teal. Y equals negative x. Y equals negative x looks like y equals x, but it's negative x, so it's going to be going in this direction. So there's my function there. And we can extend it to the other side, and you'll see why I'm not doing that in just a bit. But I'm going to label this here as y equals negative x. And notice that we're going from x equals 0, so x equals 0, so x equals 0. Well, 0's here, so it looks like I'm trapping myself or restricting myself there, and it looks like I'm going all the way to 1, right? X equals 1. So it looks like I'm looking at this little region right here. So I'm trying to find the area of all of this here. Well, to find the area, we saw in the previous video that you really just have to subtract your upper curve, the area of your upper curve, minus the area of your lower curve. Well, let's go ahead and do that in this problem here. So we have, let me go ahead and set it up. We have that the area, and what we can actually do, if you think about if we go back to talking about Riemann sums and we talk about rectangles, you can think if I were to draw, let's say like a rectangle here. So if I were to draw a rectangle here, well, what would be the width? The width would here be the width of the rectangle we can call delta x. The width of this rectangle we can call delta x, but what would be the height? Well, the height here, the height from, oops, let me go ahead and erase this. The height from here all the way down here, so the height of the entire rectangle, let me call this y1, so my y function for y1, and let me actually label this as y2. But the height of this rectangle, you can think about this. For example, say this is like a number, pick any number you want, like 5 or something, and this was 3, then the total height would be 8, right? The total height would be 8, or you could think about it like the difference between these two functions here. You could say maybe y1 minus y2. That would be the height of that rectangle. So you would really subtract. So for example, again, I can maybe make a concrete example here. I can say, like, for example, assume that this height like is, say, 3, since it's very close to 2. Say it's 3. We don't know for sure. And let's just say that the height here, or this bottom piece here, since it's negative, let's just say it's negative 3. Well, what would be the total height here of the rectangle? Well, that would be 3 minus a negative 3, which would give you a 6. So here we're going to have y1 minus y2, since we really don't know what these numbers are. I mean, and if you notice, every rectangle we draw will have a different height. For example, I can draw another rectangle over here with a width of delta x, and notice the height here would be different. The height here would be different than the first rectangle that I'm shading in right now, right? So again, we can set this up as our first function, so our upper function, as x squared x squared plus 2, and we're going to subtract, right, the area of this rectangle. I do y1 minus y2, so I'm going to subtract minus my bottom function, which is just negative x. Now this right here is the height, so this is the height of our rectangle. So this is the height. This is the height of our rectangle. But again, the area of a rectangle is length times width, so or length times height. So this is our height, right? It looks like I'm missing my width, but remember, my width is given by this delta x. Now, if you think back to Riemann sums and adding up a bunch of rectangles and finding the limit of these rectangles as the number of rectangles goes or grows to infinity, that's an integral right there. So really, if I want the actual area, so if I want the total area, this is just going to be equal to the integral. And again, we're going from 0. Remember our limits here, we're going from 0 to 1. We're going from 0 to 1. And then now I'm just going to have my two functions, right? The upper function, which is, let me do this in green. Give me 1 second. My upper function, which is going to be x squared plus 2. And then we're going to take away this bottom function, minus x. And then we tag on our delta x, which in this case it's dx, as the rectangles are getting infinitely thin. So we have this integral that we need to take care of, and this is a pretty straightforward integral to do, but this will give us the entire area underneath, or the area in between these two curves here. So let's go ahead and evaluate this. I'm going to clean this up a bit. So again, it's going to be the integral from 0 to 1. And I'm going to have, let's see, I'm going to have x squared plus 2. Now here I have a minus negative x. That'll turn into a positive x. So that'll turn into a positive x. And then I'm going to finish this off with my dx here. So again, not too bad to integrate. I'm going to scroll down a little bit to give us more room. Okay, so if I find the antiderivative of this thing, so again, it's going to be 1/3 x cubed plus 2x plus a half x squared. And remember, we are going from 0 to 1. So what does this equal? Well, actually, instead of working to the side, let me go ahead and work. Let me erase this and let me go ahead and work down instead. So if I plug in my upper limit, I'm going to have, let's see, I'm going to have 1/3 times 1 cubed plus 2 times 1 plus 1/2 times 1 squared. And then I have to subtract and plug in the 0. But notice that if I plug in the 0, everything will go away. I mean, 1/3 times 0 cubed is 0, 2 times 0 is 0, and a half times 0 squared will be 0. So I really don't need to substitute the bottom limit. I can just evaluate this, and 1/3 plus 2 plus a half. If you do all the arithmetic there, you should get a final answer of 17/6. But this 17/6 again represents the area in between these two curves right here.